So my next question is, how could I make this more accurate? How could I make this more accurate? Because at the moment it's not very good, like I'm massively overbuy. What could I do differently if I wanted to go back and get an even better approximation? Sorry? What is the answer? We don't know at the moment. We'll go back in just a second. Okay? At the moment my guess is 39. But what could I do differently about how I calculate my areas? Well, at the moment, I'm just saying the width of my rectangle is every 1, okay? What if I changed it? What if I changed it so the width of my rectangle was every half? Are you happy that if I changed it so it was every half, suddenly then I get an even better approximation? Can you see that? I'm just basically making the width of my rectangle smaller and smaller and smaller, okay? So let's think about what I've actually done here, right? I have said that I'm just going to add together loads and loads of rectangles. I'm going to add together loads of rectangles. Now, just because I'm lazy, I'm just going to use a bit of notation here. I'm going to write that. I'm going to write that. What does that mean?
I think that's a sign for integration.
No, it's not. It's not quite. It does mean sum, okay? It's literally the capital letter S in the Greek alphabet, sigma, okay? Which is for sum. It just literally means add loads of stuff together, okay? Well, what am I going to add together? What am I going to add together? First of all, I'm going to move across through all of these different x values, okay? So what I'm literally going to do is I'm going to move across by all these different x values, and I'm going to stick these x values into my function. That's going to give me the height of the rectangle. Does that make sense? So I'm basically sticking in all of these different x values into this function, and that's going to give me the height of all of these different rectangles. Does that make sense to everyone? Yeah? So I'm literally going to stick my x value into this function, x squared plus 4. Okay? And then I'm going to multiply that. I'm going to multiply that by my width of my rectangle, the base of my rectangle, if you like. Okay? Now that base of the rectangle, for the moment, I'm just going to call some change in x. Because are you happy? All I'm doing here is just moving across by some value in the x direction. In this case, it's just 1. Okay? So I'm moving across by some change in x each time. Okay? So I'm going to multiply it by whatever my change in x is. Remember that symbol there?
Change.
Exactly that. It's Greek letter delta, right? For difference. It means change. Good. But then you've just told me to get an even better approximation of the area, I am going, oh, by the way, where do I start from? Where do I start from?
Left.
Yeah, from the left, which is -2. Where do I finish up at? 3. Okay, so I need to put my bounds in here. I need to say start at -2 and finish up at 3. Okay? Okay, fine. So this is an okay approximation of the area, but if you want an even better approximation, how could I do that? It's to do with this change in x. If I make the change in x even smaller, then I'd have an even better approximation of the area. So it'd be really, really small rectangles. Does that make sense? So in other words, if I make the change in x approach 0, okay, then I can say I get an even better approximation of my area. But are you happy that the best approximation of my area is when that change in x is basically 0? In other words, it's so small that it's basically just the width of a straight line. Yeah? So when that happens, I'm saying that's the limiting case. I'm going to change my notation on here just to illustrate that. Okay? So instead of having a capital letter S to illustrate a big change, in other words, I'm summing together things which are quite big, I'm going to say I'm going to sum together things which are really small. So I'm just going to basically elongate my S in the English language. So instead of writing an S like that, I just elongate it and make it look like that. Okay? I still say I want to start at the same point, so I still say I want to start at -2 and finish up at 3. Okay? My height of the rectangle is still going to be given by this, so it's still going to be given by x squared plus 4. But are you happy now? I'm not going to be multiplying by a big change in x. I'm going to be multiplying by a change in x that's so small that it's basically 0. You remember on this side when we were looking at differentiation, when the change in x or the change in y is so small that it's basically 0, I change my notation from a delta to a d. Okay? So I'm literally going to write some ridiculously small change in x. Okay? So this looks a bit weird. Has anybody seen that before? Yeah? This looks a bit weird, but it's literally just this same idea in the limiting case. In other words, where the change is so small that it's basically 0. So what I'm literally doing here, if I make a quick copy of this diagram again, so I've got my curve, got my x-axis, okay, so this is y equals x squared plus 4, okay, and I've got my 2 points on here, so I've got -2 and I've got 3 over here, okay. I want to work out the area. What I'm literally doing is instead of using these big rectangles, these big old rectangles which are rubbish approximations, what I'm doing is considering rectangles that are so small they're basically 0. In other words, like loads of little tiny rectangles stacked on top of each other, which of course you can just realise is essentially just a line. Okay? When I do that, that means that my rectangles are going to give me the best possible approximation of this area. Does that make sense? Okay.